Hello, so in this video we'll try to solve a simple optimization problem, and we are trying to find the dimensions of a rectangular prism which yields the highest volume to surface area ratio. Okay, so what is the application of it? That if this guy is large, it means we can have higher capacity for smaller amount of material amount of material. Okay, so this should not be actually cube, this should be actually a rectangular prism. Okay, so now if we have a rectangular prism something like this, so this is my, let's say this is my H, this is my B, and this is my L. So this is the length, breadth, and edge. So without loss of generality, I can say this length is some multiple of this B. Okay, I can call it this R. Okay, and again without loss of generality, I can also say R is greater than or equal to 1. Why? Because if R is less than 1, then I can say this as B and this as L. Correct? And then this becomes the same ratio. Okay. So now let's define our volume and let's define our surface area. So our volume is what? Our volume is R times B times H, which is this guy. What is our surface area? Now we are assuming that the box is open. And the same kind of analysis can be done for a closed box, but we are doing it with, the intention is just to see the procedure, how can we arrive at the right result. So then we have the area of the base, which is R, so this is RB times B, which is RB squared. Then 2BH, so B times H is this guy and this guy, and then 2 times RBH, so RBH is this guy and this guy. Okay, so this is the surface area. So now if I write this RB squared in terms of V, then this becomes V over H. So then since V is equal to RB squared H, then RB squared, this is equal to V over H. Okay, and similarly if I write this B, so what is my B? So from here my B is V over RH square root. Okay, so if I plug this B is equal to V over RH square root, I will get this guy. And similarly this guy, here also I have plugged in B is equal to V over RH. And then after that, so let's simplify this guy. So then this H and this H, and then this H and this H. So then we have square root of H outside, and then square root of B, square root of V outside. And the only thing which remains is 1 over R square root and R square root. So this is my surface area. Okay. So now, so our intention is to find H for which S is minimized for a fixed V. Okay, so what do? We find d over dh of S. So this is equal to this guy. So then this is equal to minus V over H squared. Then I can say plus 2 times root V times 1 over 2H, and then 1 over R plus root R. Correct? Because the differential of this guy is this guy, and the differential of this guy is this guy. Okay, and then we say set to 0 to find the critical points. So if we do that, then we have what? Then we have 2 times root V. Then this 2 and 2 cancels out, so I don't have to write 2. And 2 root V over root H times 1 over R plus root R. This is equal to V over H squared. Okay. Okay. So then what can we do? we can bring this h squared here and this v root v here. So this becomes root v and this goes. And this goes and this becomes h to the power of 3 over 2. Correct? So I can say h to the power of 3 over 2, this is equal to root v divided by 1 over r plus root r. Okay. And then I can plug the value of v, which is equal to r b squared h. This is over 1 over r plus root r. Okay. So then I can say h to the power of 3 over 2, this is equal to root r times root h times b over 1 over r square root plus r square root. Okay. Now this goes and this goes, because this is half and this is 3 over 2, so this becomes just 1. Okay. So my final equation is this h is equal to root r over 1 over r plus r b. So this is the relationship of h and b for which the surface area is minimized for a fixed v. Okay, and I can simplify this more. I can say this h is equal to r over 1 plus r times b. Okay, so this is for any base, any kind of base here. But the question is, what is the value of r? What is the value of appropriate r? So then we will say, and by the way, before we go there, this you can say that you can actually easily check that this guy, this guy here is actually a minimum point, because you should take the double derivative, so that you can say double derivative is positive. This means that it's a minimum. Okay. Okay. Anyways, so then the question is, what value of r minimizes s? Now note that here. So if you note it here, I have r here and r here, and I have r here. So if we have, since it's only related to the base, if we have this guy, so this is well-known fact that the amount of perimeter is minimum for a fixed area when we have a square. So then this means r is equal to 1 minimizes the perimeter here. Okay. So if I put r is equal to 1 here, so r is equal to 1 in this guy, so I can say h is equal to 1 over 2 b. Okay. So what is the conclusion? So conclusion is that the maximum VSR is when base is squared, base is a square, and height is half the base. Okay. Okay. So this was a very simple optimization problem we have solved. Actually, this is a minimization problem, which is in my opinion, it's an application of the differential here. So this is the application of this formula that you can differentiate and set it to 0 and find the right answer. So this is it for this video. Hope it was easy to understand. Thanks for watching and hope you like the video.